Hi guys, welcome to lab number 9 of GG497 Geological Visualization. This week we're going to learn how to draw faults in cross-section, and that takes us to Wincanton. And the Wincanton stratigraphy is, pretty straightforward. You can see from our outcrop patterns that the Cretaceous chalks, you see how they're parallel following the ground contours almost. They're pretty flat lying, a little bit of dip. They're overlying over an angular unconformity the Jurassic stratigraphy, which are in these browns and oranges and yellow colours. But what I really want you to focus on in this map is this impressive, really whopping, great long fault called the Mia fault, which runs almost over the entire length of the stratigraphy. Now what you can see along the Mia fault is, if we're sat in the Cretaceous chalks, if you follow their outcrop patterns, their contacts, you can see that they are cross-cut by this fault. They abut the fault and then they stop. They've been truncated. So what's happened is, after these Jurassic rocks have been deposited and the Cretaceous rocks have been deposited, that whole area has been faulted. It's undergone some sort of tectonic activity that's manifested itself as this Mia fault, and it's brought much older rocks from the Jurassic upwards so that they are then juxtaposed next to the Cretaceous rocks. So as ever, we have a couple of questions that ask you a bit about what's going on in the map. Then we'll have a little structure contour exercise to see if you can understand the attitude of the Mia fault and its sense of displacement. Then to reconstruct the geological history of the area. And you've been provided a hill profile which tries to show, or what you'll complete in order to show the subsurface geology and what that fault has done at depth. Okay, so see how you get on, and as ever in the next little part of the video I'll go through my process for tackling a cross section in a region such as this.
Coca candy straight from Japan, hologram, and she was never as think you know what I need to get by. Something for your...
Welcome everybody to the Wincanton sheet, where we're going to see how faults present themselves on maps and how we can draw them in cross-section. If we look at our map, we can generally split it into two different rock packages. The oldest rocks in the area are these browns and oranges, which are Jurassic in age. And then these greens are the Cretaceous greensands and chalks, which we've already seen on the Sidmouth sheet. Now the contact between these younger Cretaceous rocks and the older Jurassic rocks is interesting. In different places on this map sheet, sometimes the contact between the Cretaceous and the Jurassic is unconformable. And you can tell that it's an unconformity because the stratigraphic contacts that you can follow within the Jurassic rocks, when they get to that contact with the Cretaceous rocks, they just stop. So we have an example of it there, and we have an example of it in the north. But in other places, the contact between the Cretaceous rocks and the Jurassic rocks is bounded by this sizable fault which runs across the sort of middle northeast to southwest orientation. It's called the Mia fault, and generally if faults are a big deal, if they've got significant displacement, they end up getting a name. So whenever you see a fault that's got a name, the chances are it's a big one. If it's a little fault, then people tend not to name them so much because they're largely insignificant. But this Mia fault is a big deal. Okay, so that's sort of the general structure. We have one package of rocks which unconformably overlies another package of rocks, but in other places those rocks have been faulted into contact with each other. But if we just have a little look at the stratigraphy themselves, if we look into the Cretaceous rocks, you can see it's got those very characteristic outcrop patterns which are parallel to the ground contours. So they look like they are horizontal in terms of their dip. And if you look around this area, it's very sparse in terms of dip measurement. So in other words, the geologists who mapped these couldn't find any dip. Therefore, I think both of those bits of evidence are good to suggest that our Cretaceous rocks are almost perfectly sub-horizontal, whatever you want to call it. If we look at our if we look at our Jurassic rocks then, we can see somewhat similar outcrop patterns where some of the contacts, they're a little bit, so they're kind of parallel to the ground contours in certain areas, but in other areas they form these sort of strips. And indeed, if we look around these Jurassic rocks near to where we see the strip-like outcrops, you can see that they've recorded a very modest amount of dip. For instance, in this region of the map, they're recording 4 degrees dip towards the northeast. Just over to the west, they're recording 5 degrees up to 12 degrees. And then in the northwest of the map, they're recording a dip of about 4 degrees. Okay, so they too are relatively horizontal, but they do have some measurable dip, which is largely missing in the Cretaceous rocks. So what I've done is use my tape to mark on the 2 corners of my cross section, here at 750270 and then here at 830350. And you can imagine that if we were to cross that cross section in this orientation, we'd go through our conformable Jurassic rocks, which are dipping along our section at about 4 degrees towards the northeast. Then we're going to cross this Mia fault and then head into the flat-lying Cretaceous greensands and chalks. So the dip of the beds, that's fine. We know that the Cretaceous rocks, they look like they're flat-lying, at least in our area of our cross-section. And we've got this dip reading on our conformable sequence of Jurassic rocks, which says that they're going at 4 degrees towards the northeast. Now the one thing that's unknown is the dip of this Mia fault. And there isn't anywhere along this fault that gives you an angle of dip, but there is other information. The first thing is the outcrop pattern. Look at this outcrop pattern. Look how it wiggles and is deflected across the contours. Remember, if this was a steep fault, if this was at say 60, 70, 80 degrees, then it would be a perfectly linear feature. But the fact that it's got this sort of circuitous route, this almost meandering path across the topography, that indicates that this fault is at a relatively low angle. We can't say for certain what that angle of dip of the fault is yet, but we know just from its outcrop pattern that in all likelihood it's relatively low angle. If you look along the fault, you can also see that it has a tick on that fault trace that's pointing towards the north. And if we look at what that tick means in the key, we can see that it says it marks a fault with the cross mark indicating the down-thrown side. So what this tick is telling us is that these Cretaceous rocks on the north, that's the side of the fault that's been pushed downwards, and the south side of the fault, where we can see the Jurassic rocks, that's been pushed upwards. So the north has gone down, the south has gone up. Now also along this fault, if you look closely, in a couple of places you should be able to see the letters RF. There's one there, and there's one there, and I think that's about, there's two of them. There's two of them that you should be able to see. So if you zoom into your map, you should be able to see RF printed next to the fault plane. Now if you look back at the key, you should be able to see that RF indicates a reverse fault. So the geologists who mapped this did a fantastic job. They've got a really good fault trace that you can follow. They've worked out which side has been thrown down and which side has come up. And they've also been able to work out what the type of fault is. In this case, this Mir fault is a reverse fault, which is different to a normal fault or a strike-slip fault. So this fault they've worked out has had an element of dip-slip, and that dip slip has meant that the north side of the fault has gone down relative to the south side. So just to recap, we're going to, as we draw our cross section, we're going to go through our conformable Jurassic sequence, then we're going to cross this reverse fault, then we're going to enter our flat-lying Cretaceous green sands and chalks. So I think we've got an understanding of what's happening in this map, and now what we're going to do is start collecting our data. Here we are, zoomed in onto our cross section between our 2 points, where we're going to go through our dipping and conformable Jurassic rocks that have a dip of about 4 degrees towards the northeast, cross our reverse fault, and then head into our flat-lying green sands and chalks of the Cretaceous. So I've got my little strip handy, and now I'm going to start by going along that cross section and marking all of our contacts and structures and information, things like that. Okay, so starting with the Jurassic then, we've got a contact between the Oxford clay and the lower calcareous grit, and then we're into the coral rag, and then there's an upper calcareous grit. Then we're into the Kimmeridge clay with a bit of calcareous sand on top. Yeah, and I think that calcareous sand is flat lying, so the outcrop kind of bends across the topography like this, with a little bit of coral rag again. And then right there at the end there's a contact just before the fault of some more upper calcareous grit. Let me just put that back in the right place. Yep. Okay, then what we've got is, let's make that one a little bit bigger so that I know it's a fault, so I'll treat it slightly differently than the others. Then from there to there we're into our, I think it's our upper green sand. Yep. Then we've got a little bit of lower chalk with the top of this little hill being middle chalk. Then we're back into lower chalk, middle chalk, and then unsurprisingly we're in upper chalk all the way to the end. Okay, so these colours are going to test my palette, and indeed I had to even go into another box of pencils. So let's see how far I get. We've got an A, that's our Oxford clay. Then we've got thin little bit there. I'm really going to have to pay attention to which colours I use. So I'm just marking on this thin veneer to show what rock types I'd go across in this area. Then here and here all the same. And then I'm pretty sure that this unit here is G11 D, which is our coral rag, and then we've got some of our coral rag there. And then this G11E is also here. Okay, now that's a very, very, very defined palette of browns and oranges. So I'll have to pay attention with labels there, because there will be some of us, and myself included, who don't necessarily distinguish all of those different shades of brown. Then we're into our upper green sand. Lower chalk. Middle chalk, and then our upper chalk. Great, so those are all of the stratigraphic contacts marked on. Then what we can do is include something about our dips. And we know from the outcrop pattern that these Cretaceous chalks, they're all flat lying, no dip. But our Jurassic rocks, if we were just to move this section slightly, we can see right on our section line, very close to our section, there's a 4-degree dip, and it's perfectly parallel to our cross-section line. You see the direction of dip here is to the northeast, and that's the same orientation as our cross-section line. So therefore, for the dip of these beds, we don't have to calculate any apparent dip. We don't, because we're taking our section perpendicular to strike of the beds. So we can just record these as having a 4-degree dip. Okay, our fault though, that's a different matter. And we can record some of the information about that fault. First thing that we can say is give it a sense of movement. So if we pull our cross-section strip away, you can see right here, there's one of these little ticks which says that the north side of the fault, the Cretaceous rocks, they're the ones which have gone down, and the Jurassic ones are the ones which have gone up. So I can show that the movement along this fault is going to be this side has moved down and this side has moved up. And then what I can do is just check to see if there's any information I'm missing. I've got my stratigraphic contacts, I've got my dips, I've got my sense of movement on my fault. But what I could do, particularly because these colours they're quite limited, is I could include their symbols. So this little band here in the code is G11E. This band, this darker orange, is G11D. This brown right at the end is G10. So that would make this one here, if we look at the stratigraphic column, G11A. So 1, 2, 3, 4. Okay, so now we're up to here. And this one, this dark brown, has the code of G12. Then we're back into G11E, and so is that one, G11E, and in between them is G11D. Then we're back into G12 with this little bit of G11E at the end. God, that's all quite difficult to say, but I think at least recording both the colour and the stratigraphic code, it'll allow us to join these things back up in the cross section. Okay, labelling our Cretaceous rocks then, we've got H4, our green sand. Then we go into our lower chalk, which is H5A. Then a little bit of the middle chalk is exposed, so H5B. Then we're back into the H5A, H5B is there, and then finishing up on H5C. Okay, so that's all of the data collected for our cross section. We've got the structural information, we've got the positions of the stratigraphic contacts, we've got the fault. So now I think what we can do is go to our cross section and start drawing that stuff in cross section view. Okay, so here we are on our hill profile, and this is our cross section strip that we've collected our data from. So what I can do is start transferring that data from our strip onto our cross section panel. So what I do is line up A and B as our two extremes of our cross section, and then go along and mark on at the base of our cross section all of the points that we've crossed. So I'm going to count this as F, so I can tell them apart from the stratigraphic contact, and then just mark on all of the others that I cross as I go along my cross section. Okay, there they all are at the bottom, and then what I can do is move all of those vertically upwards so that they hit our cross section. And what I'll just try and do really quickly is buff my protractor a little bit, because I don't want any grime off that protractor getting onto my cross section. Okay, so I line up my protractor crosshair with my point, and then I just mark on the surface wherever I get one of these stratigraphic contacts. There's one there, and there's one there either side of this little hill. There's another one there, and then my fault. That's about there, so I'll kind of mark him a bit bigger with an F. So I know that he's important. I know that he's important later. And then we've got one there, and then we've got a couple of thin ones about there and about there. And I would say he's about there and there. And again there and there. And then moving across the end of the section, we've got another contact there and another contact there. Okay, then what we can do to make us feel like we're making progress, we can transfer some of those colours. So let's start with our darkest G10, just marking on a very thin veneer on the surface. Use a light orange to show where G11A is, and then it's a very dark orange to show G11D. Then we've got a medium orange for these outcrops of G11E. So there's one there, one there, one there, and one there. So it's all these little skinny ones. I bet they're going to link up across our section. Looking at them. Then we've got a bit of G12, which is in a medium brown. And then we've got a little bit of slightly darker brown to give us our G11D. And then we've got another medium brown, or a lighter brown rather, to give us G12. Okay, I might just mark on very lightly some of these so I can tell what it is I'm looking at, because my colour recognition of these isn't fantastic. E, 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 and E, and then this one is G12, G12, and this guy in the middle is G11D. Okay, and then moving this side, our green sand. Then in dark green we have our lower chalk H5A. And then H5C, which is our upper chalk, is in there. And then let's see if I can use this colour to distinguish sort of the middle chalk. Okay, So that's, if we were to walk along this landscape, that's where we'd hit these different geological contacts. The next thing that we need to do is figure out which things we're going to plot first to save us having to rub anything out. And what we should do is look back at the map to refresh ourselves about the cross-cutting relationships. You can see that we've got Carboniferous rocks, you can see that we've got Jurassic rocks, and you can see that they've all been cut by this fault. So the youngest thing, and the first thing that we're going to plot on our cross-section, is this fault. Then we're going to do the contacts of the Cretaceous as the next youngest thing, and then the contacts of the Jurassic as the next youngest thing. Okay, so we're going to start by plotting this fault, this one here. But we're going to have to do a couple of calculations first, because part of this question asks you to plot this section with a vertical exaggeration, and that's because a lot of these rocks in the map area, they have horizontal, or they have relatively low dips. So in order to stretch that stratigraphy apart, we need to introduce a vertical exaggeration. The other problem we've got is that our cross-section line plots at an oblique angle to the strike of the fault plane. The fault plane strikes something like this, sort of east-west-ish, and the cross-section line runs northeast-southwest. So because we've got this oblique angle to strike, our fault is going to have an apparent dip. It's not going to look as steep along this cross-section because we're not cutting it at strike. If we had drawn a cross-section at an angle like this, where we did cut the fault perpendicular to strike, then we'd see the true dip. But because we have this oblique angle, we're going to see an apparent dip along that section for the fault, and we're going to have to calculate what that apparent dip angle is. Okay, so two things to take into account: the vertical exaggeration and the apparent dip. Okay, so this is when we break out a notepad where we can do some maths. And now we're going to calculate the how much this vertical exaggeration has will have modified our dip. Okay, so you guys hopefully remember from the labs that the formula for an exaggerated dip is equal to the inverse tan of the tan of the true dip multiplied by the exaggeration factor. Okay, so what we can do is substitute our values into this equation and solve the exaggerated dip. So you guys hopefully remember from question 5, the previous question in this lab, that the true dip of the dike, we've calculated that as being 36 degrees. And the exaggeration factor that we're using for our cross section is an exaggeration factor of 4. So what we can do is calculate the tan of 36 degrees, multiply that by 4, and then take the inverse tangent of that answer. So the exaggerated dip for our fault is 71 degrees. Okay. Now this is the angle that we'd plot the fault at if we had drawn a cross section perpendicular to strike. So that true dip of 36 degrees, if we were drawing a cross section perpendicular to strike of the fault with this vertical exaggeration factor of 4, we'd end up drawing the fault as 71 degrees. However, because of our oblique angle between the fault plane and our strike and the cross-section orientation, we need to turn this angle of dip of the fault plane into an apparent dip. Okay, so what we'll do now is that calculation, and that calculation works as the tan of the apparent dip is equal to the tan of the true dip multiplied by the cosine of the difference between the cross-section bearing and the dip direction of the fault. Okay, so what we can do now is substitute in some values. So the tan of the apparent dip is equal to the tan of the true dip, which we've just calculated as being 71 degrees, and then multiply that by the cosine of the difference between the cross section and the dip direction of the fault. So the dip direction of the fault we've already calculated as 182, and the orientation of the cross section, if we go back to the map, our cross section line runs in this orientation. So using my protractor and lining it up on a grid square, the corner of a grid square, I can count around clockwise 1, 10, 20, 30, 40, 0, 4, 6. So the bearing of my cross section is 0, 4, 6. Okay, so to simplify that down, the tan of the apparent dip is equal to the tangent of 71, which is 2.90, and then the 182 minus 46, if I take the shift, if I take the cosine of that answer, that comes to minus 0.72. Okay? Then if we simplify down further, we can do this negative 0.72 multiplied by 2.9 gives us minus 2.09. And then what we can do is calculate the apparent dip by taking the inverse tangent of that answer to give us the inverse tangent of that answer to give us an angle of 64 degrees. So even though when we take into account the vertical exaggeration of our fault, its dip would be 71 degrees, because we've got
an oblique section to this fault, its actual apparent dip on the cross section would be 64 degrees. Okay, feel free to rewind that step a couple of times to make sure that it makes sense, but all we're doing is a simple mathematical equation to change the true dip of our fault to an apparent dip, because we're drawing basically our cross section at a slightly funny angle. Okay, but now back to the cross section. What I can do is then put my protractor on my cross section and then draw my apparent dip of the fault at 64 degrees. I know the dip direction is towards the south, which in this case is towards our Jurassic rocks. So I'm going to count round 0, 10, 20, 30, 40, 50, 60, 64. So my fault plane on my cross section is going to look like this. Then what I can do is start plotting some of my younger rocks, because I've just done this fault, so I'm touching up the colours there a bit. So then what I can start doing is plotting some of the geological contacts on my cross section. And as ever, we start with the youngest things first. So why don't we start by plotting in these horizontal. Oh, that's almost horizontal. These horizontal chalks going from contact to contact where it allows me to. I know the angle of dip is horizontal based on the outcrop patterns. And then I'm going to leave it there for a minute. We'll tackle this bit in a moment. And I know that the Jurassic rocks, they too have an angle of dip. On our cross-section strip, we worked out that that angle of dip transferred from the map was 4 degrees. But just in the same way as with the fault, we're going to have to change that angle of dip to take into account this 4 times vertical exaggeration factor. So again, if we go through that calculation again, the calculation for an exaggerated dip is such that the exaggerated dip is equal to the inverse tangent of the tan of the true dip multiplied by the exaggeration factor. So our exaggerated dip is equal to the tan to the -1 of our tan of 4 degrees, that's the dip of our Jurassic bed, multiplied by the exaggeration factor, which is 4. So doing that calculation, tangent of 4 multiplied by 4, and then taking the inverse tangent of that answer gives us an exaggerated dip of 16 degrees. So that 16 degrees allows us to turn what would be dipping at like 4 degrees into something that's dipping at 16 degrees, which will allow us to see it. Okay, so let's start plotting on that geology then. So moving along, we've got all of these G11Es, so they're all the same rock type, so they should all join up at about 16 degrees. So going from there to there to there, oh magic, I love it when that comes together. If I put all of those in one, you can see how those bands of G11E all of those bands of our upper calcareous grit, how it's actually the same layer, we're just seeing it in multiple places because of the topography. Okay, then what we've got is this is G11D and this is G11D as well, so let's line up our contact there, and we're drawing it at 16 degrees. So this will come down, this will come down like so. And then I'm going to stop it at the fault, because you guys know by now that faults, they're a slip surface. So this contact, as soon as it gets to the fault, it's going to have been displaced on the other side. And then this bottom contact of G11A is going to continue like so. And then we don't actually see the bottom of G10, but looking at the stratigraphic column, it's quite a thick bed. So if I broke out my ruler and calculator, I could calculate the true thickness of that bed. But what I'm going to do to show my level of uncertainty is simply dot in or dash in where the base of that bed could conceivably be. Okay? Right. Why don't we add some colour into our Jurassic rocks? Because we've got the boundaries in now. And those aren't going to change. If we were to be stood on the surface and drill down the dip of these beds, we're confident that we'd stay in those beds until we hit that fault plane. So why don't we just colour in these rocks? It'll fill in a good portion of our cross section. We're sure of it, as anybody reasonably can be. And it's basically completed a big chunk of our cross section. I think there's something must be under this piece of paper that's dragging these marks through. So that's our G10. Then our G11 is a sort of fairly light orange, or G11A. And then our G11D, that's a much darker colour. Fantastic. And then our G11E is another sort of, I think it's a bit of a lighter orange. And then our G12 is a lighter brown. Great, and then what we can do is beneath the G10, the next unit that we've inferred the depth of here is the G9, which is Cornbrash, which is a limestone. So I'm just going to mark that on like so. Okay, then what we can do is add in the colour for some of our Cretaceous rocks. Like of the ones that we're certain of. So for instance, we know from the top of this hill, I've used the wrong green there. From the top of this hill is ringed by the upper limestone. Oh sorry, the upper chalk. Then beneath that we have a layer of this middle chalk. which is also on the knob of this little hill. Then under that we have the lower chalk, which I picked the wrong colour for again. This is the lower chalk. And then under that, up until basically the base of this valley that we can be certain of, we're into the green sand. Okay, at this point we're left with this page of blankness where there's not going to be a cavity there. Oh, I don't know, maybe because it's chalk. We're going to have to fill in some geology. So looking at our stratigraphic column, we can estimate the thickness to which the upper green sand would continue downwards based on its thickness in the stratigraphic column and its relative thickness to the other unit. So I think a reasonable thickness for that H4 unit, that upper green sand, would be something like this, and I'm going to use my pencil to dash in the base of that contact and then apply some colour because I'm brave and I've committed to it. Then, looking at the stratigraphic column, beneath the upper green sand I can see a relatively thin bed of what they call silty clay, which has got the symbol H3. So if I were to dash that bed of silty clay in, and then that's kind of got this sort of teal, I guess, colour, but I don't have any teal, but I do have a blue. I can dot that in. Okay. Now this basal contact that I've just drawn, if you look at the stratigraphic column, is actually an unconformity. So now what I have to do is try and understand what the geology beneath this Cretaceous unconformity is going to be. I know that if I were to drill down through the Cretaceous, through the unconformity, sooner or later I'd hit the Jurassic rocks. That's what the stratigraphic column tells us. But without knowing how much slip has occurred along this fault, I can't be certain at the moment where these dipping Jurassic rocks would be beneath this unconformable surface. I know that the right hand side of the fault has been shifted downwards relative to the left hand side, but I don't know by how much. So what I'm going to have to do is take a geological guess. So why don't I just start plotting, say here for example, the contact between G12 and G11E. So at 16 degrees there, which is about that point, is that about 16? Yeah. I'm going to say that there represents dash it in, represents this upper contact between G12 and G11E. And then under it I'm going to put its basal contact. Okay? Then under that I'm going to be in G11D, so let's assume that these rocks have a constant stratigraphic thickness, so it's 2 centimeters thick on my section. There it's at 2 centimeters as well. So between those 2 points, that's where I'm going to interpret where G11D exists, and then G11A would plot about here. Now you're probably at home thinking, well, how have you got there? And what I would say to you is that I don't know what is beneath this unconformity based on the data that we've got. I don't know the exact positions of these beds. I know that they'll be there because that's what the stratigraphy is. We've got Cretaceous rocks sitting unconformably on top of Jurassic rocks. I'll know they'll be there, but their exact position of where they'll crop out beneath the unconformity is based on my best guess. Okay, so if we were to colour that in then, all of this material is going to be my G12s. Then I've got this, let's do the G11D first, is all this material. Yeah, then let's put in the bottom of my G10. And then we've got this lighter orange there, and this sort of more yellowy orange there. Okay, so that's my best interpretation that I can come up with for the subsurface geology. There's a lot of solid lines of which I am sure, based on our information on the map. And then there are more dashed lines which are more interpretive. Now what I'm just going to do to help people tell these apart is highlight my unconformity. Give it in green. And then the other thing that I would like to do is to plot that fault in, let's use a red so that we can tell us apart. Let's give that fault some extra importance just so we can show that it's not a stratigraphic contact. And then what I can do is continue the geology above the surface to show where it would have been prior to modern erosional processes. So that's my fault and my unconformity. Then what I should do is mark on my horizontal rocks as the next youngest thing. Showing where they'd be prior to modern erosional processes. And then this upper chalk I'll leave as is. It doesn't really have an upper defined end in the stratigraphic column. Then these Jurassic beds, we can plot those in. And to finish off with the base of this G11A. And I think that's a pretty good interpretation for our cross section. We've shown the subsurface geology and we've indicated the level of sureness that we have for some of our contacts. So now what we can do is move on to our housekeeping process and tidy this up for final presentation. Okay, the first thing that we should do in our housekeeping measures is to figure out what our scales are. Now, just as the same as all of the other maps that we've created in this course, by moving data directly from the map onto a strip of paper, and then from that strip of paper onto our cross section, we don't change the horizontal scale. So our horizontal scale is the same as the map scale, which is 1 to 50,000. But our vertical scale, on the other hand, we've exaggerated everything by a factor of 4, so we can pull out these thinly bedded horizontal rocks. So our vertical scale, because we've exaggerated it by 4, for every unit we go in the vertical, we're seeing 4 times less than the horizontal scale. We're seeing a distance of 4 times less. Okay, so our vertical scale then is simply our horizontal scale, 50,000, divided by 4, which gives us a vertical scale of 1 to 12500. Okay, and then we can maybe put in brackets 4 times vertical exaggeration. Great. Then what we could do is maybe, because these colors are so dreadfully similar, maybe what we could do is label using the symbols in the key, so G9, G10. This unit here, if we get rid of the labels on the ground surface, that should give us a bit more room to write things in. This unit here is G11A. Then we're into G11D. Let's get rid of these temporary labels that I left on the surface. They were helpful at the time, but now their time is over. This unit here is G11E, and then this is G11F. Then in our chalk, we're up to H5C. This unit is H5B, H5B, and then this unit is H5A. Then we're down to H4, H3 just above the unconformity, and then these rocks. I guess we don't need to do this because we've already shown what the colours equate to on that side, but just in case anyone is confused, we can quickly put those in. G11A, and then finishing with G10. Okay, so that's all labelled. And then what we can do is quickly add in a key. So we've got 1, 2, 3, 4, 5, 6 for the Jurassic, and 1, 2, 3, 4, 5 for the Cretaceous. So why don't we just do here are our chalks. Turn those into boxes. So we've got that's our H5C. This is our H5B. This is our H5A, I might have used the wrong one there. This is our H4. And then I used the blue for H3. So H5C, H5B, H5A, H4, H3 equate to the silty clay, the upper green sand, lower chalk, middle chalk and upper chalk. And then we've got one, two, three, four, 5, 6, 7. And then here we can do the key for the Jurassic rock. So at the top of our Jurassic, we've got our G11F. Then we've got our G11E. G11A is in a lighter version of this orange. So G11F, G11E, G11D, G11A, G10 and G9. I thought we had more units than that. So I'm doing my dark brown. And then a lighter one for G9, and then labelling these up is the corn brash. Then we're into the Oxford clay, lower calcareous grit, coral rag, upper calcareous grit, and the Kimmeridge clay. Kimmeridge clay. Okay? So by doing this cross section, we've been able to show a reverse fault, one where the footwall has gone down, hanging wall has gone up, and we've shown how in cross section stratigraphy that abuts a fault can be truncated just like it is on the map, and we've employed some vertical exaggeration to pull the stratigraphy apart so you can actually see the thicknesses of the rocks, and by doing that we've had to modify some of the dips of the rocks that we plot on our geological cross section. So there's quite a lot going on in that cross section, but hopefully you've understood it. Feel free to watch this video again. And I'll see you next time for where we look at unconformities on maps. Alright, thanks guys. Keep washing those hands and stay safe. I'll see you in a little while.